Hello, and today we're looking at areas and lengths in polar coordinates. So the idea is we have a region that's going to be within some curve in polar coordinates. We want to find the area. So the general idea is we want to find the area of each of these, we would call these sectors, right? These little slices that we're approximating um, almost think of like pizza slices, right? So if we have all those sectors added up, all those areas, that would give us the area underneath the curve. So we have a formula for that, and the formula is we have area, and we're looking at we go from alpha to beta. Okay, so basically that's the area between, we have the one theta and the other theta, so we're going to go between here and here, and we follow the formula. We have 1/2 r squared d theta, and we try to integrate that, and then we plug in the bounds at the end. Okay, so for this one, example 1, find the area of the region in the xy plane enclosed by the cardioid. R equals 2 times 1 plus cosine theta. Okay, so this is the regular cardioid that we know of as 2 plus 2 cosine theta. Okay, it's beneficial to factor out the 2. Okay, so when we plug it into this formula, we're going to plug it in and square it. And when we square it, it's easier to square something with less coefficients in front of it, right? Or smaller coefficients. Okay, so now if in terms of our alpha and our beta, we're going to do the full cardioid, right? It's the area of the region enclosed by the cardioid. So when it's the full cardioid, we're going to go 0 to 2 pi. Okay, so those will be our bounds. So we'll have 0 to 2 pi, 1/2. Okay, our r squared. So we're going to do 2, 1 plus cosine theta, and we're going to square this, and then d theta. Okay, so we're going to simplify a little bit. We have 1/2. Now when we square this, when we square the 2, we get 4. And then when we square 1 plus cosine theta, 1 plus cosine theta times 1 plus cosine theta, that would be 1 plus 2 cosine theta plus cosine square theta. D theta. Okay, so that means if we have the 4, what I could do is pull the 4 out with the half. 4 times a half, that's 2. So I'll have 2 times 1 plus 2 cosine theta plus cosine square theta d theta. Okay, I could distribute the 2. Now when I distribute the 2, I'll have 2 plus 4 cosine theta plus 2 cosine square theta d theta. Now the cosine squared, when I go to integrate this, that's not going to integrate, right? Because that's going to be like chain rule, and we don't have a sign next to it. So we're going to convert the cosine squared into one of those identities, right? So we know from somewhere that cosine squared theta is equal to 1 plus cosine of 2 theta over 2. Right? So we have integral 0 to 2 pi of 2 plus 4 cosine theta plus 2 times, so we're going to replace cosine squared with what we have here. So we'll have 2 times 1 plus cosine of 2 theta over 2 d theta. Okay, so when I multiply by 2 here, the 2 and the 2 here, they cancel. Right, so I have 2 plus 4 cosine theta plus 1 plus cosine 2 theta. The 1 I'll combine with the 2, so that'll make it 3. So I'll have 3 plus 4 cosine theta plus cosine 2 theta. Okay. So now from here I can integrate these, right? So when I integrate, I have 3 theta plus integral of cosine is sine, so that'll be 4 sine theta. And then again, integral of cosine is sine, but this will be chain rule here, so I would have to offset that, so that would be plus 1/2 sine of 2 theta. And I'll evaluate this 0 to 2 pi. Okay, so plug in the 2 pi. So we have 3 times 2 pi plus 4 times sine of 2 pi plus 1/2 sine of 2 times 2 pi, which is 4 pi. Okay, minus 3 times 0 plus 4 times sine of 0 plus 1/2 sine of 2 times 0, which is 0. Okay, well, the second part, sine of 0 is 0, so 3 times 0 is 0. These are all zeros, so we don't have to worry about that. Sine of 2 pi is 0, right? Same as sine of 0, so this is a 0. Sine of 4 pi is 0, so that's a 0. So the only thing left here would be 6 pi. Okay, and that would be the area of the region enclosed by the cardioid. Okay. Okay. All right, let's take a look at our next topic, area of the region between two curves. So if we have, in this sense, an outside curve with the R2 and an inside curve that's shown with the R1, we would do this formula for figuring out the area between those curves. Okay, so similar formula with the 1/2 and the R squared, except now we have R2, the outer one, minus the inner one. Okay, so you have to determine what are the outer ones and the inner ones. Okay, so let's take a look at Find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Okay, so to get a sense of this, let's draw the graph. Let's draw the cardioid. Remember, this would be 1 minus, put the 1 in here if it helps you to picture it. This will be based off of the x-axis because of the cosine. We're going to add 1 plus 1. And because of the minus here, it'll be on the left side of the x-axis. 1 plus 1 is 2, so I'm going to go out to 2. Now this gives me the intercepts on my opposite axis. So on my y, I go to plus 1 and minus 1. And then for my other point, I do 1 minus 1, which is 0. Okay, so this will be a cardioid. Okay, and the cardioid would look like this. Okay, so that's the cardioid. And then the circle of r equals 1, it's a radius of 1. So circle of radius 1 would be that. So they want the area of the region that lies inside the circle and outside the cardioid. Okay, so inside the circle and outside the cardioid, that's going to be this region, outside the cardioid and inside the circle. Okay, so now for our bounds, we're going from, well, these are thetas, remember. Our bounds are going to be from here to here. Okay, so this will be pi over 2 as a theta, and this would be negative pi over 2. Okay, so originally we could set this up as, something like this. We would say area is pi over 2 to negative pi over 2, 1/2, and then we would do the r2 squared minus r1 squared d theta. Okay, now one thing that's nice about this is a symmetric graph. The top half is going to be the same as the bottom half. Okay, so we could ideally go from pi over 2 to 0, and then we just double it. And then that would give us, so we could do pi over 2 to 0, and then we double it. Like that. Okay, so let's set this up. So our outer curve would be the r equals 1. Inner curve would be the cardioid, 1 minus cosine theta. Okay, so now we know what we have to do. Okay, so let's do that. Now what happens immediately as we notice this, because we got this 1/2, when we bring that out, it's going to cancel with the 2. So we don't have to end up worrying about that 2 later on. This 1/2 we're going to bring outside, it's going to cancel with the 2. Okay, so let's go ahead and start our problem. We have pi over 2, 0 to pi over 2. And then we got 1 squared, which is 1, minus 1 minus cosine theta squared and d theta. Okay, so we got 0 to pi over 2, 1 minus, again we want to expand 1 minus cosine theta, so that would give us 1 minus 2 cosine theta plus cosine square theta. Okay, so the 1 and the minus 1, they'll cancel. And we have a negative here that's going to distribute into the parentheses. So a negative of a negative 2 cosine, that will just give us 2 cosine theta. And a negative of a positive will be minus cosine square theta. Okay, so next step, we want to be able to rewrite the cosine squared because we cannot integrate it, right? We would need a sign attached to it because of chain rule. So we want to rewrite cosine squared as a different identity, right? And we did that earlier. We had cosine squared theta equal to 1 plus cosine 2 theta over 2. Okay, so we're going to replace cosine squared theta with 1 plus cosine 2 theta over 2. Okay, so we have 2 cosine theta minus 1 plus cosine 2 theta over 2. Okay, next step, we want to integrate this, right? So we have 2 integral cosine is sine. Now here we have a minus 1/2, so when we integrate this, that would be a minus theta over 2, or 1/2 theta. And then we have another minus, because this minus will affect the cosine as well. So we have a minus. And then here we have to use the chain rule. So we already have a 1/2 in front. To offset the 2 theta, we have another 1/2, so that would be 1/4 sine of 2 theta. And we would evaluate from pi over 2 to 0. Okay, so now let's plug in. We would say 2 sine of pi over 2 minus pi over 2, 1/2 pi over 2, so 1/2 of pi over 2 minus 1/4 sine of 2 times pi over 2 would be just pi. And then we would say minus 2 sine 0, sine of 0, minus 0 over 2 minus 1/4 sine 2 times 0 is 0. Okay, so sine of 0 is 0, like we mentioned earlier. This is 0. And so we're left with what we have up here. Sine of pi is 0, so that's gone. So we end up with sine of pi over 2, which is 1. So we have 2 times 1, which is 2. And then here we have minus pi over 4. Okay, and that would be the area. Okay. Let's take a look at another one. Example 3, find all the points where the curve r equals 2 cosine pi over 3 intersects the circle of radius square root 2 centered at the origin. Okay. The curve r equals 2 cosine pi over 3. So because we're looking for intersection points, right, we have r equals 2 cosine of theta over 3, and this would be r equals square root of 2. We set these two equal to one another, so we have 2 cosine of theta over 3 equal to square root of 2. And we solve this, right? We can solve this for theta. So if we first divide by 2, we have cosine of theta over 3 equals square root 2 over 2. Then we can take the inverse cosine, right, or the arc cosine of both sides. And then same thing here, take the arc cosine of both sides. That'll leave us with theta over 3. Now, let's think, the cosine of what angle is square root 2 over 2? Right, that should be an easy one. That would be 45 degrees, or pi over 4. Okay, so now to get theta, we have theta over 3 equals pi over 4, so multiply both sides by 3. So we get theta equal to 3 pi over 4. Okay, we get 3 pi over 4. Now that's going to be one of the intersection points. Now, what we also have to consider is that anytime we have a circle, right, r equals square root 2, there's another version of the same circle, right? If we say r equals negative square root of 2. Okay, so for that reason alone, we have to do this a second way to get the second point of intersection. Okay, so we'll do that down below. So we have 2 cosine of theta over 3 equals negative square root 2. Okay, so that tells us that we get cosine of theta over 3 equals negative square root 2 over 2. Take the inverse cosine of both sides. Now, which angle gives us a cosine of negative square root 2 over 2? Right, so what does that give us? So that would be if we end up with third quadrant, right? So third quadrant would be, if we have 3 pi over 4, 3 pi over 4 would be here. That means we would go down in here. So that would be, what would that be, 9 pi over 4? Right? So that would be 9 pi over 4. I should say we have 3 pi over 4, but then we're going to do something, and we're going to multiply by 3. So 3 pi over 4 multiplied by 3, went ahead of myself a little bit. So theta would equal 9 pi over 4. Okay, and that would be the other point. Right? Okay, now 9 pi over 4, we're going to end up 9 pi over 4 actually is not this point. 9 pi over 4 is going to give us, that's going to wrap around and give us pi over 4, right? Now, the only problem with that is the cosine of pi over 4 is radical 2 over 2. So what we'll do is we'll reflect it. We'll end up with 5 pi over 4. That's what I was thinking of earlier. 5 pi over 4. So that ends up actually producing that point. So we have the 2 points. From the first one we have square root 2. And then this one will be square root 2 . And then from the first one we have square root 2, 3 pi over 4. Okay, let's take a look at our next example. We have length, so arc length, if you will, of a polar curve. Okay, we follow it with this example. Okay, we have the function itself plus the derivative of the function with respect to theta squared, all under a square root with respect to theta, and we try to integrate it and then plug in the bounds. Okay, so find the length of the cardioid. R equals 1 minus cosine theta. Okay, so we know our R. Let's take the derivative of R as our first step, dr d theta. So the derivative of negative cosine would be sine. Okay, so we get that part set up. So we're going to do r squared. So we'll have, let's set that up. R squared would be 1 minus cosine theta squared. Let's simplify that. That's 1 minus 2 cosine theta plus cosine squared theta. And then we got to square the dr d theta. So dr d theta squared would be sine squared theta. And so we're going to add these together, right? Because this is what's going to go underneath the square root. So we have r squared plus dr d theta squared. So that's going to be 1 minus 2 cosine theta plus cosine squared theta plus the dr d theta squared, which was sine squared. Now look what's nice about this. We have one of our favorite identities. Cosine squared plus sine squared is equal to 1. So we take that 1, right? This becomes 1. We take it, add it to the 1 in the beginning. So we get 2. So 2 minus 2 cosine theta. That's what's going to go underneath the square root. Okay, now because the whole cardioid, we're going to go from 0 to 2 pi. Okay, so the length, we're going to go from 0 to 2 pi. And then we did all the work for the r squared and the dr d theta squared. So it's going to be square root of 2 minus 2 cosine theta d theta. Now, this isn't going to work out nicely as a square root of this integral. So we have to get a little creative with this. We're going to use an identity to swap out the 2 minus 2 cosine theta. Okay, so I'm going to do that on the side here. So you remember how we swapped out for cosine squared a lot of times? Well, we're going to do almost like a reverse, but for something that has 2 minus 2 cosine theta, or at the very least, if we have 1 minus cosine theta, because we could factor out the 2, right? So one of those identities that has 1 minus cosine theta, but not exactly, right, would be if we had the sine squared identity. Right, sine squared of theta equals 1 minus cosine of 2 theta over 2. Now, we don't have cosine of 2 theta here, we have cosine of theta. Okay, so what if I adjusted this formula and I said 1 minus cosine of theta over 2? Then that would make this become sine squared, if we keep the relationship between the thetas the same. Sine squared would be theta over 2. Right? It would just be half of theta. Okay? So now, if I'm multiplying both sides by 2, I get 2 sine of theta over 2 equals 1 minus cosine theta. Put the squared there on the sine. Okay, so that's what I'm going to replace now. Alright, that's going to go right in there. Okay, so I have integral 0 to 2 pi. Inside the square root I have 2 times 2 sine squared of theta over 2 d theta. Okay, so the 2 and the 2 gives us 4. We have 4 sine squared of theta over 2. And this nicely we could take the square root of. Right? Square root of the 4 sine squared would just be, square root of 4 is 2, square root of sine squared is sine. Okay, so we would do 2 pi, 0 to 2 pi of 2 sine Normally we put absolute value here, but remember the sine of theta over 2 is greater than 0 for theta being between 0 and 2 pi. Okay, so now let's integrate this. If we integrate the sine, we get negative cosine. Now it's a theta over 2, so we have to factor in that 1/2 has to cancel with the 1/2, so we have to multiply by another 2. So this is going to end up giving us negative 4 cosine of theta over 2. And we'll plug in 2 pi to 0. Okay, so we got negative 4 cosine of 2 pi over 2, that would be pi, minus negative 4 cosine of 0 over 2, which is 0. Okay, well, cosine of pi is negative 1. Cosine of 0 is 1. So we have negative 4 times negative 1 is a positive 4. And then we got minus a negative 4, so that's plus 4. So we end up with 8 would be as our length of this arc. Okay, so that's it for today's lesson. Any questions, just write me an email or ask during the lecture. Have a good day, have a good night. We'll see you soon.